Yeah, so Chris Forrester, is the CEO of a company called Hypernym, and she will explain what Hypernym does because it's quite complex, and I don't want to just simplify it in few words. And she has been in the tech industry, in the scene of tech for many years, many years, and she has done really interesting stuff from different generation of technology. So now she's into AI, and she has done some groundbreaking work on AI. And therefore, the Hypernym, the company, which, if I simplify it, it's more the semantic processing of the prompts and the output, and she will explain what that means. But that is so promising that Hypernym is one of the few companies that were selected by Meta in their startup cohort. So Chris has some very interesting ideas on how to improve the current LLMs through algorithm that she has written, and she will explain that. So Chris, please take it away.
Thank you very much. That was actually a really awesome intro. Thank you, Vinish. So yeah, I'm Chris, CEO of Hypernym. Here today to talk to you about semantic technologies in general. So I'm just going to take a breath. I usually talk really fast, so I'm going to try to be a little bit more approachable for this particular session. So our work is in language. Our work is in words. The awesome part is that these large language models that have come out over the last 20 years, I would say probably development research 2018, so we're almost at the 10-year mark. It's very interesting how quickly time passes, so about 8 years now. And these technologies are language models. These are large language models. So these are as big as your hard drive ever has been in the last like 10 years. You got an entire binary blob, just a single file that you could transfer. You could share it with other people if you wanted to. Heck, Meta's technologies are able to be shared. Cohere's technologies. Cohere was very early in to being able to be have these particular language models shareable, open for the world. But that also meant that all of a sudden we started to have these things going everywhere. So anywhere that AI could touch, all of a sudden we had large language models a little bit behind it. And this has only grown in prevalence over the last few years with companies like Salesforce and Intel, any of the customer support bots that I'm sure that all of us have the pleasure of dealing with over the last few years. A lot of them have just been large language models repurposed. So these things are awesome until they actually have a problem. Once they're actually within their training set, once a language model actually knows what it is that it's supposed to do because it's been trained on these things 1,000 times in 1,000 variations, well, it might as well be an operator's manual. And that operator's manual is obviously made out of language. Each individual word within that operator's manual, if you're trying to do it perfectly for a human being, guess what? You're going to have to repeat yourself. You're going to have in your summary, here's what we're going to take a look at today. You're going to have an expansion within that. Here's what that particular summary meant. Then you're going to have links. You're going to have to say, here's the references to what it is that I'm talking about. And here's these big keywords. Maybe you even have an appendix where you have a bunch of jargon that then has to be translated. All of these are deadly for large language models. And the reason why is because the attention mechanism, as you're growing the number of words that you're actually adding together, all of a sudden things start to happen inside of it. All of a sudden the ability for it to actually pay attention to every single what we call token in this, which is a slice of a word, you could say. Every single token that we actually use gets added onto this particular stack. And that big file that I was saying that you could actually transfer to your friends, well, that works really well for probably 1 to 3 messages, just 3 messages off of the top of it. After that, it starts to degrade. How it degrades and why it degrades is still a little bit of a mystery, but that's where a company like Hypernym comes in order to try to take a look at what's actually going on behind the scenes, produce a little bit of what we call inspectability, and to use our techniques and evaluations to actually get to the root of the core of the problem. And this is what I'm going to be showing you today. So it's a pleasure to introduce myself to everybody, and I think I'm just going to dive right into the meat of it.
Yeah, just one comment, Chris, that usually the audience is quite well educated on AI, so you could go deeper if you wanted.
Very well. I think I will. So I'm just going to open up a very quick screen share on my computer right here. in order to get a couple of documents up there. 1 second. Make sure this is working perfectly. Great. Cool. Wonderful. So I'm just going to rest it right here. Actually, I might as well just do this for 1 second. This is my thing. This is my webpage. Anybody wants to take a look at it? I'm just going to leave it rested up here just for 1 second for LinkedIn. Obviously, all these will be shared afterwards as well. So let's dive into the meat of the magic. I'm gonna show you guys a quick presentation that is that my some of the rest of my team actually came up with as we were trying to present what part of our technologies could mean. There it is, and this is all about aligning intents. So you remember how I was talking a little bit ago about how difficult it has been to program these large language models. Well, one of our specialties is being able to actually do this correctly and to actually be able to take a look inside of them. And this is sort of what it looks like a little bit. I'm going to go into a little bit more of a deep dive into what these individual facets could mean when we're actually talking about large language models or what's actually going on. And I'm going to be getting into a lot of the applications as well that we're actually working on a day-to-day basis. So what is the weight of the word? A weight of a word is, it could be all the way from how it is that you say pleasantries in the morning to how it is that you respect your boss in the middle of the day to how it is that you're asking the lunch attendant or exactly what kind of sandwich she loves to prepare and what kind of things that she can make you in order to have you have your best day. So a lot of impetus. There's a lot of context behind every word, and there's a lot of us trying to need to only say the shortest words possible in order to get the greatest effect. Why? Because this is optimal communication. So we can do two things really well from the core of Hypernym's technology. One of them is the aspect of actually building in and actually unpack what an individual statement has to say, like an individual paragraph, and decompose it into component elements. And when we've decomposed it into component elements, when we've said, hey, we want 1,000 words and we want to move it into like 500 words, and we say to the LLM, what is it that you think is the most important pieces? All of a sudden, we start to get 1 million answers. And this is very familiar to anybody who's actually had an LLM either behave or misbehave on them. And then you say, hey, how'd you get to that answer? Wow, you got it. You nailed it perfectly. You got this entire function. How'd you get there? And it's like, oh, I made it up. And it's like, but we've had this conversation before. You weren't able to get it to do that before. What's happening? It's like, oh, and this time's magic. That's it. That's basically the answer that you get because they actually make up their reasons as a post process. They don't actually know what they're doing ahead of time. It's just pattern matching as it's rolling. But afterwards, all of a sudden they have 20/20 insight, like the most bravado of any human being that you've ever met. So we use this to our advantage. We on the left-hand side here, we have what's shown as basically a dartboard. I'm going to show you guys a very quick version of the larger version of this. Here's a bigger version of it. Here's a more scientific instrument. And what we can show in here is that we've got our basic structure, which is to enable us to have 1 million different trials of this individual word. So this is just one particular sentence. This is from one single vertical slice of Hypernym's core technology. And functionally, what it is that we end up with is we end up with a series of measurements. And one of the things that we actually were able to do within Hypernym's core technology stack, one of the things that we're actually really proud of is that unlike a lot of the existing measurements out there right now, which has math eval sets, you've got science eval sets, you have the ability to do like tool using eval sets now. All these eval sets are very specific purpose form. And all of them have a very, very, very solid thing at the very base, which is the baseline answers. So once you have a baseline answer into your set, then all of a sudden you can start doing really cool measurements. But what happens when you don't have that measurement in the first place? What happens when you have a technology that you're like, okay, this is the core of measurement, it's not to be measured. And this is what we sort of ended up with. So what it is that we're doing, and I kid you not, is we're not trying to actually, in this particular example, measure the veracity of an individual statement. We're not actually trying to measure how many keywords it has inside of it, what the information content is, really anything like that. We're actually looking at what the LLMs deal with under the hood, which is the cosine similarity. So this is going to get a little bit math nerdy for a second, but if you can imagine my two hands have the ability to either have a 1.0 if they're pointing towards each other, or a negative 1.0 if they're both facing in the same direction. All that we're doing under the hood in terms of any of this stuff in machine learning is just figuring out what the relative orientation is. So if it's looking like this and my hands are pointing in the same direction, guess what? This fact is not aligned. All of a sudden, however, if my hands, in this example, are pointing together and you get a perfect 1.0 similarity, all of a sudden these things are the same, at least to the machine learning knowledge semantic representation, which happens in an embedding space. And this is very critical to make a second point. The measurements are happening in an embedding space. The embedding space is not necessarily the same embedding space that the LLMs are working in directly. So OpenAI could have its own embedding space, and OpenAI's models, whenever you're sending in text, are turning it into its embeddings. So its embeddings are very separate than any other embeddings. You have OpenAI's embeddings, Snowflake's embeddings, etc. And the interesting thing is that within each of these embeddings, it's going to actually have a very similar way of being weighted. And this is where Hypernym's weighted its words come in. But at the same time, it's not really what we're measuring. What we're actually measuring is the results of those words, the results of those interactions. When we're actually checking of how well the answer did in an eval set, we're not even looking really with an OpenAI's embedding set. We might be looking in BERT. We might be looking in, I don't know, naming some of them off the leaderboards right now, GTKE, whatever you call it. But all of these individual embedding sets aren't necessarily in the same level, but they're all doing the exact same thing. They're all doing the exact same thing. And when you have something that's doing the exact same thing, all of a sudden you can start to measure it if you're really clever. And so here, again, we're not doing any tests on politics. We're not doing any tests on anything that you would have an actual baseline veracity. So this isn't math. This isn't science. This is not like a biology test. What we're actually showing here in this particular image is a political speech. This is actually a political speech from one of Trump's rallies from before the election. This is a political speech that actually means more than one thing at the same time to different audiences, depending on their context. It's a fantastic and wonderful use of human beings' energies in order to cohere this type of impression. And the impression is that something needs to happen. This is something like a Trump rally. This is like where he's trying to incite the populace to make a decision, to make America great again, to like whatever. This is actually just the impetus. And so when we're running this thing through an LLM, our technology, the weighting of our words, we end up with this in front of the screen right here. We call this a dartboard. Each one of these individual trials right here, to get into the meat of it, are an individual attempt at compression. So as I said before about 5 minutes ago, LLMs actually have a wonderful ability to make up why it is that they came to a specific conclusion. But if we can actually pause time, if we could actually freeze the representation just for a second and actually do the measurements ourselves, we end up with actually something like this, where most of the time, what it is that they're actually coming up with, if I can go into our primary algorithm here. So Hypernym is very straightforward. It's like JPEG for text. We have a central primary anchor, a central primary topic, a central primary hypernym, literally, in the actual context. This is 5 to 6 words. In this context, we've got political rally for national revival around the midpoint. The left to right here is just compression ratios. It doesn't really matter. Our compression is just targeting 0.5 in order to provide a measurement because you have to pick a number. So we just decided to fold it in half, like any good space analogy. And fundamentally, it does about 60 tries. Each of those tries is measured a whole bunch of times in terms of how it is not just actually compressed, but each of the individual recompositions at the end of the day. So where these individual bars are coming from any of the scientists, the data scientists in the room, is basically we can recompose it. So we take this text, this little tiny chunk, and we take it to a completely fresh LLM and we say, hey, give it to me, re-expand it. So I had 500 words, I put it into 250 words, here's the 250 words, make it 500 again. And at that point, we're asking the LLMs like something impossible because they don't actually know how to recreate it. But as we've sort of suggested, they're experts at trying to figure out how they're actually validating or recreating it. And so when we do this 1,000 times, in this particular case, 60 times, we actually end up with most of them coming up with effectively the same thing at the end of the day, which is that it's nationalism and perseverance and adversity. We've got things like let's see here, another one, the political rally for American revival. And these are terms, right? So these are semantic terms. But the really cool thing is that because these things don't actually know how they're getting towards where it is that they're going, all of the greatest parts of the LLM. So I already talked to you a little bit about where it goes bad, right? So where it goes bad is like, oh, you're asking a question, you thought that it was at the edge of it, and then all of a sudden, boom, here's an answer that has nothing to do with what we're doing. Oh, let me just delete part of your file system. Let's see if that'll fix it. Let me simplify. Let me try to help you and simplify is a lot of the time it goes into it. And yet, The thing that we all fell in love with is that one of 1,000 tries that we tried at the very beginning, that it worked. That it worked at the very beginning. It worked when we actually gave it a tough coding problem. We were like, can these things actually do the things that it's taking me like 3 hours to manually painstakingly decompose? Yes, occasionally it did. One out of 1,000 tries that we tried it before, the reason why we fell in love was because they were operating at basically superhuman capacity for a second, for just that one try. Or maybe we even got an entire conversation where it just so happened to be constructed within our idea, where it just happened to guess the next guess, and all of a sudden it looked like magic. Well, guess what? It is magic. That's the whole thing. It is actually magic. And so fundamentally, what it is that we can do if we're able to try it over and over and over and over again is actually get the perfect answer. And this is where we actually end up with a quality that Hypernym can actually produce for language systems that is unlike anything else out there, because we can actually do this enough times with tiny models in order to get something like this instead, a nationalist rallying cry for America. So the difference here in terms of how information flows is that if you were to try to actually communicate even to a human being a political rally for American nationalism, it's a big difference to nationalistic. A nationalist rallying cry for America inspires that something's happening right then and there. It's not a place or a thing that's actually like you could go to and maybe you'd see on the news. This is something that you want to be involved in. And as soon as we're actually talking about the semantics as something that you would witness versus something that you would be involved in, all of a sudden we're on a completely different level. And this completely different level is now measurable. And this is the key, is that because we can actually measure it, and because to a human being, each of the individual outputs effectively basically looks the same, all of a sudden we can now use two facets that Hypernym can bring to us. One, this little tiny 5 words should be debuggable to a human being. And the reason why is because there's been tons of papers on this particular stuff. I can share stuff afterwards with the group on any Discords or anything. But fundamentally, we've done research, and it's basically the simpler it is, the fewer words that we're actually trying to gather, the more a human being's alignment of terms of like, here's what this means, or here's what these individual tags could be, versus an actual machine learning, they start to converge, but only when your actual set of number of words is very small. As soon as you actually are growing above it into even like a single sentence length, all of a sudden the behind the scenes things of how these individual triangles are pointed towards each other, all of a sudden they start to become too complex to recognize, and all of a sudden they start to basically all merge together and melt it together. It's difficult to figure them out. But if we can do this from moment to moment, from sector to sector, word by word, basically we can actually get a measurement of not just how LLMs perceive it, but the best way of actually perceiving it for LLMs in the future. And then we get into the next particular phase. So this was the background of what Hypernym's core technology actually was about 1.5 years ago, and how we actually sort of made magic. The really cool part here, the discovery, if I can share it with the group, so to speak, is that right now I'm showing you the recomposition effect between GPT-4o and GPT 3.5. So I'm using GPT 4o mini to make these compressions, and I'm using, in this particular example, GPT 3.5 to re-express it. But the cool part is that from our research, we actually found that it was extraordinarily generalized, where we could actually go from individual model classes to model classes. And not only would the approximate things, the best cases from even the smallest model's conception, actually end up being the largest model's actual preference as well, and the way that they actually did things with the highest semantic similarity whenever it was doing its reconstruction event. But we actually ended up with a scenario where we can actually now tell, almost like a model signature, how the models are behaving themselves. By this recomposition effect, with this actual compression structure, what it is that we're actually ending up measuring then is its total overall possible performance. And so we end up with things where we can see for models that didn't have a very good public opinion, why, basically. All of GPT 4.5's answers, in this particular case, we're looking at GPT 4.5 preview, the one that was sort of negged by the community. Yeah, well, guess what? We can see that GPT 4.1, in terms of its responses, what do these small error bars mean? Well, it means that it was more sure about the answer. Every single time that it had this compressed bundle, it was basically guessing the same output over and over and over again. This is very different than something like GPT 4.5, however, which was trained to be more creative. So you can see here, just in this particular example, that the overall total cap, the total overall, like if you had 1,000 conversations with GPT 4.5, you would get once in a while, you would get something that's significantly better than even the top end model at that time, which is GPT 4.1. However, you can also see that the error bars in this particular guy are much, 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 much smaller than something like GPT 4.5, which would indicate that a good half of the time you would end up with something that would feel worse than GPT 4.1, which is basically what we have in the industry. So this is all to say this algorithm works. And this algorithm works on not non-structured data. So it's actually an unstructured, self-supervised way of trying to figure out how the LLMs are actually recomputing what their original state was. And by being able to do so, then we're doing basically magic. And the magic is very straightforward. The magic is looking like this. I'm going to go into a whiteboard just for a second. I'm going to take a second for questions after this. There's a nice natural pause. And the structure is this. So if we have an object, and we have this one, and we're just going to have it as the North Star object, right? So this is like 100%. And then we have this particular structure, and we say, hey, of this object, how many unique strings are required in order to recompute it? All of a sudden, we have something that's actually known as Kolmogorov complexity. And Kolmogorov complexity, in terms of how it is that we work with it in mathematics, is a very straightforward way of saying, if you're able to do something like actually repredict what it is that we're actually able to think of next, if you're able to conceive of all the 7, 8 different ways of things being combined together in order to create one complete idea, if you're able to figure out the most efficient way to be able to transmit the entirety of a total package, well, at that point, you end up with actually something really cool, which is effectively the teleportation of information. Because if you can already predict what the end result is going to be on the other side, and you can do that deterministically ahead of time, well, all of a sudden now you don't need to transmit that information, do you? And that's where we end up with hypernyms. One of our primary products is compression. It looks strange. It looks like a conventional compressor type library, but actually what we're doing behind the scenes is this. We're actually trying to figure out precisely, exactly how much information we can squeeze out while retaining the top semantic similarity throughout the entire LLM stack while retaining human observability. So I'm just going to leave it over there. Is there any questions or anybody have any comments about this particular phase so far? I know that we're jumping right into the deep end of like how neural programs can actually like be compiled and decompiled on the fly, but that's why we're here chatting today.
Hey, Chris. I just wanted to confirm if I got the entire process workflow right. So let me know if I'm like wrong in understanding any of this. Essentially, what's happening here is you have some real data, and then you're using an LLM to compress it. So sort of like summarization, I would assume. And then you have another LLM recreated or expanded, like hypothetical documents do. And it's becoming like a full article from a short paragraph or a couple of lines. And then you're comparing the original text and the recreated text via semantic similarity. Is that correct?
That's correct, yeah.
Okay. And is the embedding model that you use causing any difference during the comparison here?
Only tiny jitter. So those particular key points that I'm showing you up here, we can measure it with BERT, or we can measure it with like MPE, whatever it called, MPE3. Very minor differences, and it's just about the jitter. But the cool part is that the more sure that the LLMs happen to be on their own, the more confident that they happen to be, well, they're going to be giving the same answer, which is going to end up naturally with any embedding space that you're measuring, it's going to end up as a tighter and tighter error bar. So we see all the patterns regardless of what embedding is actually being used, which makes our technique actually truly universal, which is sort of one of a kind, at least in our industry for a minute. We've got a lot of examples of individual models being able to do things like vector compression or embedding compression in order to get like a better bang for the buck. Ours is truly outside of that particular box and actually can work cooperatively as well as with all the other techniques as well.
I see. That makes sense. And the hypothesis is if you're able to do the compression really, really well, and the LLM on the other end is able to always interpret it like 100% the exact same way that you want to, like in an ideal perfect world, then you would never need the actual expanded text. You can always use the summarize or like shorter piece of text. Keep that around and like use that for questions. Is that the correct hypothesis?
That's exactly it. And the thing that you see in front of your screen right here is an example from us running basically like an integration test through a Gutenberg library. So we basically take like our baseline thing, just very conventional evals right here. Here's our engine right here under the hood. So here's like just a passage from Dracula. What is it actually turning into? Well, it's a deceptive conversation about travel intentions. So if you've ever read Dracula at the beginning, it's all about the carriage ride. And so this is, again, how to work that. Fundamentally, what it is that we get from that is we end up in this particular realm right here, where we can actually perform a full benchmark analysis. We can do an actual, and this is the same corpus. We can actually figure out how the combination of efficiencies is going to work, and then we can end up doing stuff with almost, when we're talking about the actual retriever techniques. So when we're talking about like, not what I just showed you with the political rally, but actually going into, hey, was this a math test? Was this a science test? Like, is there actually like information content under there? When we're doing our retrieval augmented generation, when we're pulling up the compressed pieces, is it actually pulling it up into a proper context, or are you losing information? Well, here's some nice proof in front of you right now with basically a one-to-one semantic similarity and 30% compression. And that's on the naive level. So that was off of the midline that I was showing you guys before. And if I can get a 30%, 40% increase in semantic similarity from those 1 out of 1,000 shots, I can do it here too. So this is baseline where I can get 30% from a retriever augmented generation eval set, but we can also go even further than that. So it's possible to go really, really, really far into being able to actually measure precisely how this stuff is actually coming up when we're actually measuring it from the eval side, which is really useful because then we can do really awesome things like safety testing out of band. We can actually do stuff like, here's an example. I'm just going to throw it up on the screen for 1 second. So this is Hypernym using a couple of its techniques in order to do better predictions, effectively applying ourselves in the inverse to the training realm versus otherwise. We're able to get an almost 20% boost from particular techniques in this field for tool use based on this particular technology, because we can now start to estimate how these things are going to behave after the fact, ahead of time, which is awesome. So we can actually do ahead of time pre-testing for eval sets using our technology as a measuring rod versus needing to go into other sets. So we're a complementary measurement that then ends up obviously refining all of the actual data sets so that we can do near perfect eval sets, as well as bring stuff into tool use here.
Wow, that's pretty cool.
So that's the first part of it. Now we're getting into the applications. Okay, ready? Okay. So I showed you guys the cool part. Again, this is the research from basically like a year and a bit ago, and then we went further, obviously. So what is further here? Well, further here is really cool because now we can measure how words are basically embodied, right? So we can take a package, we can take this particular thing, and because we can guess how it's going to be decomposed and recomposed on the other side, we can now have these really, really, really self-assured packages that are interestingly very temperature resistant. So when we're talking about temperature now, I'm just going to be really stupid for a second, just for the sake of our notes. So when we're talking about temperature in machine learning context, what it is that we're actually talking about is how random and chaotic it's actually going to respond. And this is really awesome. When you were into creative writing, you want a bunch of different variety of responses. However, when you're dealing with things like, I don't know, tool use for agents, you don't want a bunch of different responses. In fact, you want it to be as predictable and reliable as possible, following the exact same steps. Unlike you would do for creative writing, where you don't necessarily want to follow the exact same passage structure all the time. So that means that we can, so within this particular whole process, we are able to measure not just how the evolution and flow of these particular words is going on, but we're able to now deal with derivatives. So the first derivative, obviously, for Hypernym is compression. It's a very useful use case, being able to reduce things by 30% while keeping 100% retrieval augmented. Great, awesome, cool. But what do we do further from that? How do we actually measure things that are not just semantics, but actually like the other part of the world, which is the actual like causal effects? And that is that's tricky. It's very tricky. So we took Hypernym from where it is over here, and then we started to apply it into you can call it like a real world domain. I'm going to show you guys an example of how that actually looks and how that actually translates right now. Let's pull it up 1 second. This is so this is a live example, or at least it's a live data example. And this is a live data example. I've just for the data scientist nerds, I've just doubled one of the axes so that you can actually see it properly, just to get that question out of the way. And what it is it's just the hypernyms. So we took our technology and we're like, great, this thing can like actually work properly. And then we noticed that, okay, cool, we can also do this like other selection where we can obviously get these like super summaries, these anchors in latent space really well defined. Part of our process, part of the Hypernym's core vision was being able to make language that doesn't hurt, language that doesn't cause friction. And what that turns into on an application side is being able to do a message ingester. So the 1,000 messages that you're receiving today from Signal, Telegram, WhatsApp, I'm sure that you've thought about it before of like, why don't I just have one app? Why don't I just have one like way of actually like interacting with these things? So that was our core mission a couple years back. We developed this core compression technology as a nice to have. Eventually we found out that a lot of people actually just wanted the compression itself versus the core product. So we ended up developing that more. But this was an offshoot of one of our core product's goals, which is to be able to figure out how to align user intent. And when we're talking about aligning user intent, all of a sudden we're right in the heart of our current struggle within machine learning, which is how is it that I as a human being, with as few words, with as messy, sloppy language as possible, how is it that I can get my idea over to a machine learning thing where I can actually just like do the thing without me needing to be interrupted with doing it by itself? And this is a result from that. So what we did here is that we're doing message ingestion, and one at a time we're taking in message streams, and those message streams, we're decomposing it, we're turning it into this hypernym, this anchor in latent space. And because of our measurements and because of our ability to actually like perceive what's going on here, we're actually able to make a message streaming app. And the message streaming app is really cool because what you're looking at here, you could consider it to be one Slack thread. You could consider it to be one particular mission. In fact, what is it you're actually seeing right here is part of San Francisco City Hall meetings. So this is actually a public meeting, a public series of meetings and a public series of presentations that culminates at the end of the day into an actual decision by a corpus of people in the government. And so what we end up with here, this is going to be very, very familiar to everybody in the group so far. So look at that, initially about a meeting agenda discussion summary, and it became stable as a city council meeting and agenda discussion. So what we're doing here is basically we're taking each individual message, we're treating it as its own pocket universe because literally you can do anything with a message. I'm going to give one example, not to confuse the class here, but if I said, hey, everything that I just said, I just totally made up. All of a sudden, everything that I've actually, like all the information that I've pushed out, all of a sudden everything's questioned. And it's not to say that the information's not true or objectively true, but I'm certainly saying that it's not true right now, but I can do it again. I can say, oh, just kidding about it, being kidding. Or I can do it again and again and again. And so each individual message can actually do such a fundamental shift to what the semantics are that you can't even consider them to be the same universes. So we did almost a multiversal comparison here. So we took the top level of everything that came to be. We took a good chunk of the messages in the past just to maintain some particular context or whatevs, and we just treated each one as its own unique universe. And by being able to treat each one as its own unique universe and watching how the hypernyms themselves evolved from this message conversation, all of a sudden we end up with something that's very self-stabilizing. And the longer that it goes over time, the greater the percentage chance that you're actually ending up with something that's the core root of the conversation. I have it down over here. So the core root of this particular conversation for the San Francisco City planning was about affordable housing and the advocacy programs within that. So this was the entire piece of it. All these individual pieces right here are how the actual meeting is coming to be. So this is individual that are talking about the amendments. These are individuals that are talking about proposals on the comments on the amendments. So they're slightly semantically differently. And we can see in this particular thing, we've got a whole bunch of things in the center here, which is basically people repeating the exact same message, they're individuals that are signing the exact same proposals in order to show the public support for a very specific proposal. So it's actually great that they're repeated right here because it's actually adding strength to a signal that more and more people are buying into this particular thing. And we can also see that within this particular thing, we're actually ending up with, interestingly enough, things that are actually different for human beings or machine learning models to try to comprehend. And this is very important because we have over here a thread that's about affordable housing in San Francisco. And then we have other threads that are about vulnerable population and affordable housing. Okay, so for most human beings, most good human beings, you'd be like, oh yeah, these are one of the same problems, right? Affordable housing and affordable housing for vulnerable populations. Like this is the same thing. We need to target both at the same time. To a machine learning model, however, they're not. And this is very critical to understand. When we're actually utilizing these things in terms of being able to figure out how we're presenting our words or how we're absorbing our words or how our ideas are being transmitted, we can make an assumption on the human being's part, and we can say, okay, my group of people, we're doing enough media. If anybody needs to call me, they can call me on my cell phone. I put my cell phone number up there. I'm in politics. This is how I'm represented. Can you do the same with an LLM? Can you actually get it for a second opinion for it? And if you guys have been listening to me before, what does that mean when you're asking a second opinion from an LLM? From Hypernym's perspective, don't do it. That's not a great idea at all. You do not ask the LLM itself for the second opinion of itself. We do things out of band. So this is an example, excuse me, this is an example, again, of a Hypernym algorithm that we're running outside of the actual machine learning space. So we're using machines in order to focus on the embedding field. We're actually using them as almost scientific precision instruments to break into this wonderful all knowledge field of embeddings. We're using LLMs here, but we're not actually taking their word for anything at all. What we're doing instead is we're actually asking them to make this most simplified version of it. And once we've had them oriented and aligned on the most simplified version, all of a sudden now we can track the actual digression, not just in our streams, but in its. And when we actually take a look at the difference between affordable housing for vulnerable populations and affordable housing for other people, we can see that at some point in this particular conversation, it opened up and at some point it closed down. Wouldn't it be nice in the center of something that could be as touchy as something like this to actually know if the machine learnings that were actually going on under the hood, that you could imagine every single person has access to ChatGPT in the actual room. It's not like cell phones are disabled. Every single person has access to ChatGPT as they're going home, on the ride there, on the ride back. At the end of the day, when they get home and they're like, oh, this particular proposal, I can't even understand it. It has too many big words in it. Hey, ChatGPT, summarize this. Hey, ChatGPT, summarize this. This is our world that we're actually ending up with right now, is ChatGPT, summarize this. The problem here is that when ChatGPT is summarizing it and it's then giving you a randomly between what it thinks that you want to hear and it thinks that you want to hear, all of a sudden it's just flipping a coin on your behalf. But you don't know that. And because you don't know that it's actually flipping that and actually measuring the weight of your words incorrectly, potentially, all of a sudden, you don't know which path you're actually choosing. If you have an amendment that was actually created by an AI that you were going to sign, would you sign this one or would you sign this one? Well, again, to a human being, these are almost indistinguishable. To a machine learning program that's actually going to be counting the votes potentially at the end of the day, however, they're not. So being able to understand these things as quickly as possible, as efficiently as possible is very useful. And then just to lighten the mood a little bit from the doom, we're actually going to see how we can help with human beings problems too. So we're going to just jump up here and we're going to actually take a look at the edge so you guys can see my smile. It's a little bit of sneaky. So here we go here. And then we've got, oh, great. Larry's talking about the housing debates. Okay. We've got a ballot changing argument and consent request. That's interesting. Okay. That makes sense for the end of a meeting to be able to figure out your processes and dues or whatever. But it's like, what's up here though? So I'm going to just go up here and just going to tickle that. There's Larry here. What's Larry talking about? Larry's talking about political consent, and he's talking about censorship. So Larry's that guy at the very edge of a meeting where he's like, I haven't been heard. I don't feel like my community is being heard. I don't have anything to do with this. This doesn't seem reasonable to me. I want out of this. This is not a great idea. And so this is a human disruptor at the end of the conversation. This is a human being that's come into the very edge after everything's been aligned to hopefully all the other human beings and the machines at this particular point, and they're still cracking in here. And this is very unique and very interesting because if we're to try to take a look at what's important in this conversation, most of the human beings would actually be pointing to most of the majority of the conversation, but then a lot of them would be pointing to the end. So this is the fun part about actually working with human beings versus large language models, is that we actually weight not just the context and tone, but like when you speak very, very, very differently. So if I can take 1 second of just showing this. So this is how we're measuring things. You guys can obviously see that it's working fairly decently. The process here is pretty straightforward. It's not going to consume 1 billion compute hours. It's a little bit complex, but it's a bounded algorithm that we can run in linear time. What is it that we can do with something like this? So what is it that I'm actually showing you guys? Well, I'm showing you that we actually have the ability to have machines understand when they're starting to make digressions. And we can actually show that machines quite possibly can detect those digressions in human conversations faster or better than the humans can in the first place. Additionally, the machines themselves can also actually tell us when we're using this particular type of predictive technology with this type of very, very strong analytical background, when we're starting to diverge or converge in context and conversations. So what if, and this is where it gets into the meat of Hypernym's actual value offering here, what if we could actually run this as a prediction machine? What if we could, ahead of time, maybe 3 minutes, 4 minutes ahead of time, tell the people in the audience, hey, guess what? Your debate's going to go off the rails. Here's X, Y, and Z things that could happen. Guess what? If this person brings up this thing at this particular time, or this person's talking about this thing, or guess what? This topic doesn't come up. Well, we're going to have a problem over here. Why? Because we can see that the streams are starting to diverge. Some people in the audience are really talking about one part of the thing, and some people are talking about a completely separate facet. And by being able to have agents tell us this, not only can we have the choice in enabling them to potentially just act as better moderators, as more attentive listeners during a conversation, being able to isolate and redirect key points, but we can also potentially use this for agentics. And this is where it gets really exciting, especially as tool use becomes really awesome. I believe that Cohere released its first reasoning model literally yesterday. I have a cute little treat for the class at the end of the day. But this is where a reasoning model, a structure, an agentic form, a very good tool using agent could actually come in and help a lot. Because not only could it then come in and try to figure out how the energy is, but if we're actually doing different measurements of this particular structure, I'm going to show you guys the other side of the fence here. So this is the scoring system of it. So we have individuals that have contributed to threads, and all the green ones here are people who are opening up threads. So Aaron, we can tell that Aaron's a moderator already, basically, right? Aaron's starting the things, Aaron's opening stuff up. Aaron's also closing down his own threads. Not all of them. He opened up a lot more than he closed down, but he's closed down a couple of them as well. So all the green ones are individuals that are opening up threads, i.e. they're actually creating a different type of branching here, a different vertical similarity, or whether or not they're closing down threads and they're actually causing the conversation to converge back to its original topic. That could be a whole variety of factors. It could be either ignoring the message completely. It could be saying, oh, we've already dealt with it. It could be like, no, Bob's out of his mind today. Or Larry's always crazy, don't worry about him. So there's a bunch of different ways of dealing with things, but the cool part is that we can now measure impulses. And if we're taking this from 1 second from human beings, and instead we have one more entry into this row here, and it's AI bot number 1, and then the next one is crypto bot number 2, and the third one is soccer bot number 3. All of a sudden we can see that maybe the soccer bot's not that great at politics, but maybe it's an awesome listener. What happens if a soccer bot is programmed to be able to listen to politics? Well, it would probably, at least in Canada, notice that the World Cup was coming. And so if we were talking about something that has a great impulse and a great import to a whole bunch of people, where some people are simply not paying attention to it, having things for city hall meetings, for city planning, for things like giant soccer arenas opening up would be pretty awesome. So let me get back to the point for 1 second. So we're here. We're in this particular part, we're right here, we're right in the center of it. What happens if we have an agent actually work with us here? What if an agent's working with us to such a huge degree that we're not actually asking it really to predict its own event, but we're just simply asking it to tell us, when should I speak? What if the agent is even one step better than that, and you trust it enough to ask it, when should I not speak? And this is where Hypernym's context, its real actual meat, comes into play. Can you actually trust an agent to tell you when not to speak up during a conversation yet? Personally, I would say no. I wouldn't say that we are there yet. I could ask an agent if I should speak up because it's going to give me some advice, but where's its accountability if it's going to tell me not to speak up? It doesn't have any accountability. If we ask it why it did that in the past, it's not going to come up with any answer other than I did it because. So this is where we come into the actual critical core context, the communal aspect of what it is that we can actually do with Hypernym and the weight of this particular structure. What if we could give you the ability to actually have an agent drop into basically any conversation that you're involved in, any of them at all, through a spouse, loved one, to your kids' school, to your kids' parents, teacher, to your kids' friends, mom and dad, to be able to keep up with friends that you haven't talked with in 30 years. What would an agent say if it could actually take a look at all of your communication infrastructure and actually build you a graph, sort of like this, of your own life? Could it actually show when you started to take a slightly different path and didn't even recognize it yourself? Could it show you in communication streams with your friends when things started to become a little bit more diffuse? Can it show that you actually ended conversations with something like this, which is a bit of could either be a call for action or a call for compensation, or it could be a call for care. care for kindness. Could you actually figure out for all the conversations that you've left, whether or not that last person actually got it? They actually received that last particular call to action. Did you receive when it is that they poke back out? You might have gotten an email 5 years ago from a conversation that was really important to you five and a half years ago. You could have got it, never processed it, and still be carrying that around with you somehow. Okay, this is how human beings work. We don't really let go of stuff that easy. So what if we could have an LLM show us why we were carrying around that weight? I'm not suggesting that an LLM can actually take part of that burden at all right now, but I am suggesting to everybody in this particular thing that we can actually allow them to see us. We can allow them to see us through these conversations. We can allow us to see ourselves a little bit better by being able to look at this thing that's able to show us a slightly different reflection of our own selves. And with a universalized technology that's able to actually do this stuff properly, again, out of band, all of a sudden we're not needing to ask it, oh, why did you predict this? Why did you predict that? It's very straightforward to a human being. Is it the same? Is it identical? Well, we almost thought that this was identical, and I'm pretty sure that everybody in the room thought that these two threads were identical, but only one of them was talking about the housing affordability for the vulnerable populations versus the non-vulnerable populations. And that means that there's a huge potential political impetus here in order to not necessarily correct it, but to unify people around these particular contexts. So that's stage 2. This is what we came up with approximately about 6.5 months ago at this particular point. This is an experiment that we ran off of live data, basically, from the SF City Science Lab. Big shout out to Peter Hirschberg, if any of you guys know him. Great advocate in the city. So this is where we're at right now. Again, I'm going to pause for any questions on this particular piece of work.
Well, it doesn't look like we have questions, but Chris, maybe you want to kind of give an overall kind of wind down your talk. It's only 5 minutes left.
Definitely. All right. So that's what we can do with our technology, and that's how we came to get where we are today. I'm just going to do a very, very, very quick sort of like rundown, just because we've got a lot of science nerds in the thing. How does Hypernym's tech? This is our most common question. I'm just going to do this at the edge. So this is our most common question of how is it that we stack up to different other competitors? What is it that we do in our core algorithm? Well, we found that structurally, there are a bunch of different ways of asking for the same particular pieces of data. Let's ignore the purple parts for a second here. The orange parts are basically how well the models do. This is a full ensemble comparison. All the top models from the top providers I got in here. And fundamentally, they're all just asking different ways of compressing stuff over and over again. So that's one particular aspect of our particular technology. I just wanted to show the class. And then fundamentally, the last particular piece that I wanted to actually end up with, landed on here, is something for Cohere specifically. So I'm just going to show everybody a little bit of the internal structure of this, just because it's a Cohere talk, so I might as well. This is examples of our technology. I just showed you guys a dartboard from the GPT series. I wanted to show you guys Cohere so that we can edge it off here. So our lab does this all the time. We can do this for any model whatsoever. We do these particular types of analytics, and not only can we touch things in this like compressive process, but we're also expanding our technologies to doing things with like pre-training. So fundamentally, we can actually show, here's Cohere's command R+, and we can show the actual like effective error bars and scatters. And we can see that command A, we did further experiments, and we can see how tight these particular bars are. So great hats off to the Cohere team for being able to build something like this. It's pretty awesome. I do want to focus right here because we're going to do comparison. So the average semantic similarity of something between command A and command R. Command R is like pretty decent, but pretty scattered. But command A, more secure, more actual provable, has really awesome results. And then occasionally it has like really genius results as well on its side. Fundamentally, we can also detect issues. We can also figure out whether or not there's actual like scatters, different parts of the training set that are having issues. And fundamentally, I did want to show you guys this guy too, which is being able to actually detect, use cross-model comparisons. So we can actually have, for example, in this case, command A predict its own behavior and then run that extrapolation, run the recompose part through something like GPT-4.1 and actually see the difference between the cross-model comparisons between the different actual manufacturers themselves. And last but not least, this is like 12 hours ago, so I actually did want to like just land it here. for this thing in order to sort of close this off. This is what Command A's reasoning is. So this is less than 12 hours old. So this is Cohere's latest reasoning model. And we've done this test. Unfortunately, to any of the Cohere members, I need more rate limits, guys. I was able to complete literally one test before I ran out of the research credits, or the research bandwidth, really, for being able to deal with the reasoning side. Hit me up afterwards. I'd love to run more science. But the thing that I wanted to show you guys is that this particular process is getting better. So every single time, every single model increase, we are ending up with things that are tactically better, that can guess better for us, that can guess better with us. And fundamentally, this is what we're doing as a community, as a team. We're trying to bring this particular types of technologies to the world. We're actually building huge networks in terms of being able to basically get each individual part of this to everybody. And obviously, the rest of our technologies actually too large for even a single hour talk, as we can tell. We've done awesome work with Martian before. We've done work with being able to figure out how tool using agents can actually disambiguate. This is the stuff that you guys were actually just seeing. In my opinion, it's one of the biggest ones because we can actually use agentic information and agentic impulses in order to build better conversations here. Yeah, so that's the core of what it is that we do. I appreciate everybody's time today. And yeah, that's any final questions about what it is that we're up to, or how it is that we can help out the communities?
So in the final thing in Command A, it seemed like the compression and the reconstruction was quite accurate. Like the numbers were they like all above like 0.9 something.
That's right. That's right.
Wow, that's amazing.
Phenomenal performance, but we could do better in the error bars. Phenomenal performance, so yes.
So how much compression can we get today in terms of like compression ratio to like near perfect reconstruction?
Near perfect reconstruction is so it's a matter of information density. An actual here, let me show you the actual. I've got a one blip on this particular piece, I think. Yeah, it's only gonna need 1 second. Looks like this. So this is something that we did for something MongoDB on their side for embedding compression. So what it is that we've done on this side is actually tried to take a look at the amount of information itself. I like to use this as a metaphor. So basically we take information and we have the ability to squish it. We have the ability to stretch it. And once we've stretched it out enough, we can actually figure out how tangible it is and what its information structure looks like. So we can actually build all information bearing measurements and information bearing tests to actually figure out how detailed the information is as it's pulled back. Once we've done that, we actually have these individual tests of these comparisons that I was showing you a little bit before. And I don't even think I jumped to the edge of it. This is our basic compression, or our basic structure. So what it is that our algorithm does is two things at the same time really efficiently. So we're asking the LLM, hey, what's this made of? And while it's returning that, it's also returning us a sorted list of how the elements work. So we have this massive category. And then we have a list of, in this particular case, we did it like 36, 37 times. Very long context. So we can take an entire Python file, break it down into things that are reasonable chunks, and then we end up with things that are semantically similar, depending on how we're compressing it. Other algorithms do not work as well in terms of being able to maintain the actual facts. And interestingly enough, when you're asking, for example, ChatGPT to summarize something, it's actually giving you the information all basically in the same paragraph with the same density. What our algorithm does is actually picks up the salient points first. So if you just to take the top 3 of whatever 12 factoids, those top 3 will be the top 3 that are the most important to the LLM at that particular time.
I see.
Yep.
So essentially, because you're looking at the salient facts first and then doing the compression, you're able to maintain that a lot more in the final like compressed form, and so that's why like the quality comes out much higher.
Much higher, yeah. And if you consider how embeddings work, embeddings usually just chop off the edge of whatever it is that's pushed in. So our algorithm basically, even if you had like an embedding that was limited by 8192 space or whatever, you could have a massive thing. And if you just shoved our text that we had done with the compression afterwards, whatever it chopped off from the embedding would be the least salient from whatever that information content is, byte for byte, actually, word for word, token for token.
That makes sense. Yes. even like in earlier times, we were chopping off like common words, and we would like stem stuff and like remove stems and all of that. So it makes sense that you're able to just chop off non-salient features and retain a lot of like the salient ones.
Yeah, and the great part though is that it's just one shot. So the actual algorithm itself that we're running isn't like 12 individual eval sets. It's like, hey, do this one thing, and then we're measuring that one thing on that dartboard. So it's all this like crazy out of band evaluation with these really straightforward, simple tests that we can run on something like a Llama 8B model. But the really crazy part is that because the Llama 8B consumes so much less energy than, let's say, take for example, Cohere's Command A reasoning, it takes like this much energy. Llama takes like this much energy. So if we're able to actually save input tokens on the big one, that means that we're actually literally saving like massive amounts of literal compute energy at the same time. So it's actually super, super, super useful for dealing with things like one word that I can put to the class, if you guys haven't read about it, for anything like LM Studio, what is it called? They build it. Backyard AI are the two primary local ones. They built something called speculative decoding, which is actually very, 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 very similar to how Hypernym's predictive technology actually works, except that this was applied just to the actual like inference part of things. So speculative decoding actually does use smaller models in order to slightly predict the token flow of the larger ones. Once it's actually locked on, it's really cool. It's able to actually like significantly reduce the amount of energy because it's basically doing it's verifying with the big one every step as an inference step versus actually creating with the big one. It's very cool. Anyways.